So where we left off last time was I was able to create one person object by creating them in the code behind this form. I've modified it a little bit so that I can use the inputs to create different types of people based on, typing into the user interface. So I've created some input controls here where I can put in a name, choose a birth date, and enter the weight and height. And when I click the create button, then we go in here and those values from the input controls are used in my person constructor. So it makes it a little bit more dynamic. Notice that there's absolutely no validation or error handling or anything like that in here. That stuff is very important. However, you already know how to do it, so I don't want to spend our time repeating the things that we already know how to do that aren't part of the course material in this particular class. So yes, you'd want to validate, make sure they didn't leave it blank, make sure that what they entered was actually a number, and so on and so forth. But just to save a bit of time, I'm skipping over those steps. That doesn't mean that you can, though. Make sure when you submit your labs and your tests that that stuff is done. When I create the new person here, I've put their results of the toString into the text area there. And I didn't make any changes to this one. So this is great for creating one person. But now we're going to look at creating a collection of person objects. So if we want to create a collection, again, this was designed to be an interactive activity where you could choose which collection you wanted to use. So, if you put the persons into, say, a list, or you can put them in an array list, or you can put them in a hash table and choose a key, or with a dictionary and choose a key like that. We would think about how we're going to add new people and how would we remove people. Well, if we're going to remove people, we need to make some changes to our interface, because if we're going to remove, we would need a way to select a given person and then choose whether or not we wanted to remove them. So we would need to display the person objects somehow. All of them in a list, maybe you can use like a list box or something like that, where you can dynamically add or remove persons to or from the list box. And then, if you want to select one, click a delete button, things like that. Now, if we wanted to remove a person from a list, first thing I'm going to do is I'm going to declare my list at class level, a list of type person. Call it people. Isn't that funny how the IntelliSense is smart enough to know that the plural of person is people? That I find pretty impressive. So if we have a list of people here, then I don't need this at class level anymore, because I don't need any one given person to be, accessible from everywhere. I can generate the new person here, and then people.add, and add our new person to the list. So we would end up with a whole list of people here. Now, if we were going to perform the remove, I'm not going to demonstrate it during the class because it's going to take up too much of our time, but I will put it in the solution file that I post on Blackboard, so make sure you check that out when you get some time. What I would do is make sure that when I add a person, I also add them to a list box, and then I'm going to create another event handler for the list box where you can select a person from the list box and click a remove button. When you remove it, we would just use our people.remove. And, maybe we could use remove at, because I would know the position of the person I want to remove would be the same as their position in the list box. If you click the one at index 3, then you want to remove person at position 3. So that would be one easy way to solve it, as long as you keep them in the same order in both places, and you're good to go. Another way of solving it, though, would be to use remove, and you'd have to know the attributes of the person that you had to remove. So remove the person with this particular name, birth date, height, and weight. And if you want to do that, then we encounter a situation, well, what happens if we have two people with the same properties? You know, do we want to, how do we distinguish between the two of them? So then we're looking at things like using a dictionary for key value pairs, where the person maybe gets a number. And so you can distinguish person number 2 away from person number 8, even if they might have the same values in all the properties. So those are things to consider, you know, when we're working with lists and those objects. But if we're trying to find a particular person based on their attributes, then how could we determine, you know, whether one person is equal to another person? How do we find like a match per se? And this is where we get into like searching and sorting, because we wanted to determine, you know, if are we looking for just someone with the same name, or are we looking with someone with all the same properties? You know, because it's possible that it could be the same person with different properties. So for example, you know, people change their names sometimes, and you know, you might have someone where there's one name in a particular location, but you know, you're looking for a different name because they have changed their name. So you know, if you have a unique identifier for a person, then you would only have to check that value to make sure that they're equal. So things like, you know, student number, social insurance number, ID number of some sort, you know, for a vehicle, the vehicle identification number, you know, a library book has an ISBN. So there's all those different unique identifiers for objects that allow us to find matching objects, even though the other properties might be different. So, you know, you're still you, even if you change your name to something else. And the way that we know that is because of your unique identifiers. You know, at the biological level, it's your DNA. You can change your name, but, you know, a blood test will still prove that you're the same person. So when we're talking about like matching and searching for things, we have to determine, you know, if we're the creator of the person class, then we have to determine what makes a person equivalent or match another. And oftentimes it's just, well, if they have all the same properties, then they're the same person. Or we might have an ID field and say, you know, if you have the same social insurance number, then you're the same person. But we have to write rules like that about our person class, because if we don't, the system has no idea on how to compare and, you know, search for matching or equivalent person objects. And that leads us into our next set of slides. So we're looking now at slides 2, which is using contains and sorting list elements. So the contains method determines whether an equal item exists in a list. So, for example, if we have a list of employees, how can we determine if a particular employee exists in that list? And the problem is, how do we determine if two items are equal? So, in simple data types, it's easy to determine whether two items are equal. If you have two integers, then there's no ambiguity about whether integer x equals integer y, right? Is it a 2? This one is a 2. Yes, they're equal. But in custom data types, it can be a little bit more complicated. So in this set of slides, it uses an employee class as an example. You know, if you have a list of employees, an employee might have a lot of the similar parts that a person has, but they might have an employee number as well. So what are the rules? You know, are you looking for a matching name? Do you have some kind of employee ID? Or is it that all the fields have to match? So within our custom class, we want to specify what the criteria are for equality or equivalency. So in order to do this, we're going to implement an interface in our object class called IEquatable or IEquatable. The jury's still out on how we pronounce it. The IEquatable interface requires us to define a function called equals. So you learned last year about interfaces and implementing various interfaces, and the interface at its core just provides a list of rules that you can follow. So again, with the rules, right? Rules are what makes programs good. So if we implement IEquatable, it tells us that you have to define an equals function. And the equals function is a predicate function. We're going to look more at predicates later. But the predicate just means it's a Boolean valued function, true or false. So either the employees are equal or they're not. Either the two-person objects are equal or they're not. The equals function returns true if the two elements are equal and false if they are not equal. So if we want to implement this interface, we modify our class declaration to implement IEquatable with objects of the same type. So let's do that to our person class. I'm going to implement IEquatable. And we're comparing it to other person objects. Now the error here is that we haven't implemented the interface. You can use the little light bulb to implement it. And you can see that it wants us to write a method that is called equals. It returns a Boolean, true or false, and it takes as an input parameter another object of the same data type to compare with this one. So we can implement it by using that little light bulb, or you can just write it manually. Let me just squish all of this stuff up so that I don't have to scroll so much. We wrote a lot of code today. So here's the equals method. Other is an object to compare with this instance. So how can I determine whether the other person is equal to this person? And I want to return true or false. So my equals method, how do I determine whether two people are equal? Well, I'm going to say they're equal if they have the same name. I'm not even going to bother checking birth dates or heights or weights. They're equal if they have the same name. Or maybe they're equal if they have the same name and the same birth date. You know, height and weight changes over time, but you know, your birth date doesn't change. So maybe that might be a better rule. The best kind of equivalency rule uses a unique identifier, but we don't have one in our person class. So we got to make do with what we got. So we're going to return true if they're the same, and we're going to return false if they're different. So I can use an if else here, or I can, you know, do it just a shortcut of comparing them. I'll show you both ways. I'll start with the if statement. So if they have the same name and they have the same birthday, then we're going to return true. Otherwise, return false. We can shorten this up a little bit by just returning the outcome of the comparison, because the comparison itself will generate a true or false result. So if those are equal and these are equal, then we return true, determining that the two person objects, this and other, are equal to each other. There we go. And it will return false if either of those returns false. So that is a quick little way of implementing a test for equality. Now, the reason why we care about testing for equality is because we want to use the contains function. If we have a list of person objects and we want to find, you know, a matching one and see if it exists in the list or not, then we can't use contains unless we implement equals. Because if we're looking for a particular person, then, you know, this is a much more complex example. If we're looking for a particular person, then we can use the contains function. And it follows our rules to determine whether we actually find a matching employee or not. So let's go back to our demonstration here. Now that we have implemented equals, we can use our form to search the list for a matching employee, or person rather. So what I can do is I'm going to create a little search form here to see if a particular employee is in a list or not. So here's a text box, txt search name, and I'll make it nicer when it gets uploaded to Blackboard. Where's my date time picker for a matching birth date? BTP search date. And you need a little button to make it happen. Here's my search button. I'm going to type in a name and a birth date, and we're going to search to see if we can find a matching object or not. Now I have a list of person objects, and I'm going to look for a matching person object, and the way that I can do it now is I can say if my list of persons, which is called people, dot contains, and contains looks for another person item. So I have a person item here that we need to pass to contains, and when we create the new person item, the contains method uses that implementation of equals to determine whether the person I pass is the same as any of the people in the list. So the equals method that I wrote ignores the height and weight. So the thing that I'm looking for, we'll call it search, is going to be a person where we only know the height and the weight. Or rather, we don't know the height and the weight. We only know the name and the birth date. So I can use my overloaded constructor where I can ignore the heights and weights, generate a person that has a particular name and birth date, and then search for them using that equality comparer. We can make a message box to show match found, and then the else. Oops. Now, before we can do this, I have to generate some persons into my list. So when I run it, I'm going to create a few various person objects using that interface, and then we'll do the search. So this will just take a minute to load up. Now, if we hadn't implemented equals, it would have used the default object equals, and the default object matches all properties. So we wouldn't be able to find a person just based on their name and date. Using contains, we would have had to write our own manual search method, but we can use what's there and just manipulate how it works. Okay, so let's say here's person 1. Oh, I forgot to instantiate my object. Whoops. You guys see me make mistakes like this. You gotta catch me before I build. Rookie mistake, man. All right, so let's do person 1. There's our person number 1 there, and I'm gonna add person number 2. We'll give them different values here. Let's pick something different. we go. So we've got 3 people in the list now. Now the person that I'm looking for is, actually I'm going to do a 4th one. Person number 4, let's say born May 2nd, 2009. Looks good, right? So now when I'm doing my search, I find a particular matching person. I said 2009, May 2nd. It finds my matching person. If I look for something that's not there, no match. So contains is working well, just comparing the 2 values that I specified in that equals method. So this is a good way to, determine whether something exists in a list or not, while exerting complete control over how the objects are compared to each other. Not bad, right? So contains is useful for avoiding duplicate entries in your list. You can use it, before you call add, only add if the contains returns false. Just as a side note, if your list contains simple data types, like, a list of ints or strings, you don't need to specify an equality comparer for those. Contains just works on its own. It uses the object's default. The bonus of implementing IEquatable is that for your own custom objects, you get to decide how they're compared to other objects of the same type. Now, contains is a Boolean, true or false. Either the match is there or it's not. It's different from calling find. Find returns the matching element for you. So it will return an object. If you called find, it would return a person, or it would return null if there's no match. So next we're going to look about find. That comes up in the next slides. But we're going to talk first a little bit about sorting. So the easiest way to sort your list is to just call your list a sorted list. It's a different type of data structure that sorts the elements automatically. So we can create, instead of a list of person, we can make a sorted list. Now, sorted list here, we need to implement another using statement in order to get it to come in. But the sorted list, we have to tell it how it's being sorted. So we need a key here. What are we sorting by? If we have a more complex list type, we have to specify what the type of the key is. And if we're sorting by like a simple key, like an integer or a string or anything like that, then we don't have to determine how they're sorted, because integers have a default built-in way that we sort them, right? Like numeric sorting, 1 comes before 2. But if we use an object type as the key, then we would have to specify how we order those objects. So sorted list will automatically sort the list items for you, but the caveat there is that what can you specify as the key? Are we going to sort on a particular value in our object? Are we sorting persons by name? Are we sorting them by birth date? Are we sorting them by height, tallest to shortest? So we'd have to determine how we're going to perform the sort. There's also sorted dictionary. It's similar. Sorted list uses less memory, but sorted dictionary works faster for actual inserts and retrievals. There's also a non-generic version, but that is going to provide you with a whole host of issues to deal with. So how do you sort different data types? If you have a list that includes strings and integers and person objects, how do you determine what the sort order is of something like that? So, non-generics aren't great when you want sorting. If you do use a sorted list, the sort happens automatically as the add happens. Items are sorted by the key, and the keys must be unique. So if you have duplicate keys, it'll throw an exception. if you're using a custom data type as the key, you'll need to specify how they're going to be ordered. Now, we're not covering that today. It's coming up later in the term. So in this example, it is a simple sorted list. You can make a sorted list of employee names or birth dates or whatever. You just have to consider the fact that you aren't allowed duplicates in the keys. So I don't think sorted list is right for the person class, because it's definitely possible that we might have persons with the same name, and we don't want to reject those inserts. Just because two people have the same name, we won't be able to keep them both together in the same list. Well, that doesn't work out very well. So if we already have an existing structure, if we have like a list or some other kind of existing collection that doesn't sort items automatically, you can call a sort function from your list to sort the data. So in this example on the slide, we have something called names list, which is just a list of strings. So I'm going to generate that very quickly just down here so that we can, let's see. Now I'll be able to type it without getting a million error messages. So if I create a list of simple strings, and I'm going to add a couple of names. What am I doing? Oh, and let's do that. And we'll add a few names to the list. Now, if we want to sort them, these are strings. Strings already have a predetermined sort order, right? We call that the alphabet. And we know that the A name is going to come first before the B name, and that the B name comes before the F name, and the S name here will come last. So alphabetical ordering for strings is already a thing. If I call names list.sort, when we call sort, it says it sorts the elements in the list using the default comparer. So the default comparer for strings sorts them in alphabetical order. If I want to prove that it got sorted, names list, I can put the elements into like a message box or a text box or whatever. So let's build up a running string here. Oh, my bad. That's a keyword. Oh. So I need to make some way that I can make this method happen. But the output will show us that the names will be sorted alphabetically. So it reorders them using the default comparer for strings. Now, if we try to do that same thing with our person, let's use the greet button for this. I'll lose that. In our person class, we haven't specified what makes one person come before or after another. There's no default comparers for these objects. So if I call people.sort, we have absolutely no control or way to find out how they're going to be sorted. My person objects, what makes one person come before another? With strings, it's obvious. With integers, it's obvious. With any numeric data type, it's obvious how they're going to be ordered. But with a person, we haven't specified how we're going to order the elements. So calling sort on a list of person objects is not, let me turn this back to an actual list. It's not going to have that effect sorting them in the order that we want. Because what is the order that we want? We never specified. So the way to solve that is by implementing another interface called IEquatable. And we're not going to cover IEquatable today. We're going to do it, I think actually it might be next week's class. But it's similar to the way that we implemented IEquatable, where we specify how the objects are compared using a predicate function. You know, does this one come before the other one, true or false? So that's our plan for sorting. That's where we're headed, but today we're looking at using that equals comparer that we wrote. And we used it for the contains already, but we're also going to, in our next set of slides, look at how to find a matching object. So our next set of slides is about searching. So in the past, we've learned how to search data structures in two ways. Either we're using something that has a key or a numerical index to find a particular value and retrieve it. We did this way back in day one with arrays. You know, if you want the element at position 0 and retrieve that element. Or, you know, you might have performed a loop over a structure. You have a list. We're going to look at each element individually and see if it matches. And if it matches, then break out of your loop and here's your matching element. This is something that we've done a couple of times. But we're going to learn a much more efficient way of searching our data structure for a matching element. So list structures have several built-in methods that allow us to search for elements. And the first one that we're going to look at is called find. So the find method takes as an argument a predicate. Remember, a predicate is a Boolean valued function. And we're going to pass to find the name of the method that we want to use when comparing elements. So when we're searching for something, when we're looking for a match, it implies that we need to compare two things. Here's the thing we're looking for, and here's one of the elements in the list. Do they match, yes or no? And if yes, then great, here's your matching element. If not, then we go to the next element in the list. Here's the thing that we're looking for. Does this element match? Yes or no? And if yes, then, you know, here's your match, and if not, move on. So we have to tell the program the element that we're looking for, that's our search criteria, and how we're going to compare items to see if they match. So this is really similar to what we did with contains, because when we worked on contains, that returns a Boolean. Does it match or not? Yes or no? And I wrote this equals method to determine whether the element that we're looking for matches. And I said that the rules for matching are that they have the same name and birth date. That works great for contains, but contains just returns a Boolean. It doesn't actually give us the matching element. If I'm looking for a particular person in the list because I want to know how tall that person is, then contains doesn't help me. Because if I look at my design, I can say, okay, I'm looking for somebody named Molly that was born on September 20th, 1995. I want to know Molly's height and weight. So telling me whether Molly is in the list or not doesn't help me find out the data that I want to know about her. What I need is return the matching element so that I can see all of the properties. Give me Molly's record so that I can look up her other data. That's what I want. And we can't do that with contains. Contains just says, yep, we got a Molly, but it doesn't give us the matching record. So we need find for that. So there's a similarity, but it's not identical. So we start out with a list, got it, and a search criteria, got it. We want to search the list using a predicate delegate. So the function that returns a Boolean value, and we pass it as an argument to another function. So we have to tell find, here's the method that we're going to use in order to compare elements. So the delegate is going to specify how the comparison happens. We can do it as a named function, or we can do it as an anonymous function. And I'm going to show you a whole bunch of different ways to write these delegates so that we can pass them differently. You know, we can write a named method, we can write an anonymous method, we can use lambda notation, and I'm going to show you all of them. You need to know how to do all of them. On the test, I'm going to say, you know, pass a delegate using lambda notation, or pass a delegate using an anonymous function. So there's going to be, you know, you'll need to know them all. It will be on the test, I promise you. So we're going to define a function that compares the two items. It's going to return true if they match and false if they don't. That's pretty straightforward. Then we pass that function name to the find method so that the find method knows how to compare items. If we find a match, the matching element will be returned, and we'll be able to see all of that information about the matching element. So here's the steps. We've done some of them already. Create a list and populate it with elements. That's done. Define a variable to hold your search criteria. That is, what are you looking for? And then write a predicate function that will compare an element with your search criteria and determine whether or not they match. That function needs to return true or false. Then we call the find method, passing the function as the predicate, and then we check the result, see if anything was found. It'll either be null if nothing matches, or it will return the matching object. So let's take a look at some code that does this. Okay, so we're going to start by creating something that we're going to look for. Now, I can use the interface for this, but I'm going to do most of it in the code behind, just so I don't have to continually make a whole bunch of things on the interface. I am going to make a few buttons, but that's about it. So this one here is going to be the contains search. I'm going to leave that alone. And I'm going to put a bunch of buttons over here so that we can test these things out. All right. So my button click event here, I'm just going to do all of the different types of find. So we've got our list of people, and we are going to search for a particular matching name. So what I want to do is I want to write a method somewhere that is a predicate. Does it, you know, return true or false? I'm going to write it elsewhere. Private bool person to find, I guess. And in here, I'm going to create another person object. Because we're passing in something to match. Now, I called this thing name to find because I'm going to be looking for a particular name. Now, you know, for brevity's sake, I'm just going to hard code the name that we're looking for. And we're going to say, if this other person matches the name that I'm looking for, I return true. So let's say I'm looking for somebody called Molly. I'm going to say look for Molly. Now, usually, most of the time, this is going to be a variable. And I will put an example on Blackboard of it being a variable as well. That being said, we're running short on time, so I'm just going to hard code it. So if a particular person's name is Molly, then we're going to return true. Otherwise, we return false. So when I start looking for Molly, I need to call find. And when I call on find, I'm going to find a matching person. And when I call on find, I'm going to say, what method am I going to use to find matches? So this is why it's a delegate, because that's the name of the method. I'm offloading the problem to this comparer. So it's going to use this method to determine whether we have a matching record or not. If we have some person in the list that's named Molly, it's going to return that first match and store it in match 1. If we don't have any people matching that, then we'll get a null here. So I say if match 1 is null, and we can write something like no Molly's here. The else branch here, this is when we find the matching element. So now I can get to all the properties of that person with the matching name. We can do something like this. Molly's height is, and let me get my symbol here. And you can see I can get to all the properties. Oh, what am I doing? 2 strings implied. Old habits die hard, you know. Here we go. Now we can test this out and see if there's a Molly in our list. Now I have to manually generate the list first, which is sort of a pain. So I think it's going to take a little bit longer than I would hope. Okay, so let's say we've got Bob, and we've got Sam. And if I search for Molly right now, it's going to say we don't have any Mollys. But if I add a couple more people to the list, including the Molly, now I can not only find it, but get the resulting matching object. So that's our first example of using a predicate with find. Now, in the next example, let me bring up our slides here. This is another example in a list of strings. I skipped past the string example because it's pretty straightforward. Now, rather than creating our own function, another option is to create what's called a predicate object. So an object of type predicate. Now we have to specify what the underlying matching object is going to be, but we can create this object instead of writing a method and then store inside it the delegate method. So it's very similar, but just a little bit of a different syntax. So let's test this one out instead. This one is number 1, a named predicate function. Number 2 is a predicate object. So I'm creating an object of type predicate. Specify we're working with persons as the underlying type. Now, when I define the method for creating a delegate, so it's not a named method, but this part is the same. So if we look at how this method works, you can see that the input parameter is the same. I'm going to code it the same as well. I'm going to move it over here so that it kind of looks all together. It doesn't like when I format it this way until I get the other set of brackets. Now, the code inside is going to be the same as well. Now, obviously, you can make the code inside be whatever you want. But for consistency's sake, I want you to see how you can use different syntax to accomplish the same outcome. So now that I have the predicate object, I can pass that in find instead of passing the name of the method. You can see that any type of predicate in here, whether it's the name of a method or the name of the predicate objects, the outcome is the same. Either we're going to get a null or we're going to get a matching person. Option 3 is we can use a delegate method, but not create a named method. You know, this method is always generated, it always exists for the entire life of the form. Whether you're doing a search or not, it's always going to be there taking up some space. We can instead use an anonymous delegate that is called into existence while we're using find, and then after the find is done using it, it gets collected away with the rest of the garbage. So we can avoid creating this object because the object is still going to exist after. This way is a little bit more efficient, where I'm going to call find. No, not pop-up event args. I'm going to call find, but in here I'm just going to generate the anonymous delegate right in there. So I'm going to copy the code that generates the delegate and just pop it right into here. So that saves us a level, right? Move it over. I'm hoping you can see that that is the same sort of thing. You know, it's just saving a step where I'm not storing the delegate in a variable and taking up that space in memory. So I can pop that right into there. That's option 3. Option 4 and 5 use lambda expressions. And these are where this starts to get really elegant. Because now that we've got lambda expressions, I can shorten down the definition of the delegate. And you can see that that is pretty much the same as something like this, except that it's not named, right? So we're saving memory every time. You know, at first we were creating something big, and now it's just getting smaller and more efficient. But in this case, I can write a predicate object with a lambda. So I'm going to create a predicate object again, like we did in option 2, predicate of type person. But instead of writing this entire method out, I'm going to specify it as a lambda expression instead. So we're going to take in other as an input parameter, and we're going to return the Boolean of this condition here. Now that we have the predicate object, we can pass it to find. So this is another way that we can, you know, pass a function. It's just a lambda expression for a function. And maybe you can see where we're going with this. Option 5 combines the lambda with the anonymous. So I don't have to make the predicate object. Option 5 says that we're going to call find. And right in here, I can pass this directly. That shortens it up even more. This is the shortest, most efficient way to accomplish that. So I think most of the time you would be using something like this, a lambda expression with a Boolean here returning true or false. The only time you really would need to do any of the other ones is if you want the delegate to persist, like you're going to use it elsewhere in the code, you can save it as a predicate object, or If you have a method and you're using that method for other purposes, then you have a named method that you're also using in a find situation. So most of the time, it's just a quick little one-off, right? Here's my comparisons. Just do it. Find me my matching person. But sometimes you'll have a situation, where the method already exists, and you can make use of something that's already there by just passing in the name, like I did in option 1 here. Presuming the method already exists somewhere else, you can just use what's already there, and you don't have to write the lambda expression. So it really depends on what your code does and what's available to you. You want to avoid repeating yourself as much as possible, right? So those are the 5 different ways that we can call find with different types of predicates, delegate objects here. You need to know how to do them in all forms. I am going to ask you this on the test. If I say, call find with a predicate object, you want this or that. If I say call find, use a lambda expression, you got to use one of these two. All right, so that is covered by our slides here. There's a lot of different examples of searching for a particular string. This one shows you how to use the lambda expression or use the lambda expression in an anonymous delegate. Now I know our timer's up. We still want to talk about find all. So feel free to head out if you have to head out. I'm going to go on just so that we have this piece included in the video. It's probably only going to be another 3 or 4 minutes. As you might suggest, sometimes you want to find more than one matching object. If we're looking for, people named Molly, maybe there's 3 or 4 different Mollys in our list and we want to find them all. We have a function called findAll. It returns a list containing all the matches. If nothing was found, the list will be empty. That means we can check its count to see if it's 0. With findAll, we pass the same kind of predicate. So if we do a findAll, right now my criteria is that the name equals Molly. And if you use find, it's going to return the first matching object that it finds. If I'm looking at finding all of the Mollys, we can do something like this. We'll do people.findAll. And I'm going to use that same criteria here. And you can do it any of the 5 ways that I showed you before. The only difference is now we're finding a list of many matches. So if we have multiple people named Molly, we can do something like that. Or, we can use it differently. I don't want to just get stuck on this one example. We'll say short people. We want to find all people where the other height is less than 140. So if it's in centimeters, 140 centimeters is pretty short. That's even shorter than me, which is extremely short. If the height is less than 140, then they get put into that list of matches. So we can, use find all to sort and filter out certain things, right? It's fairly straightforward. Now, the last one that we look at in here, find last. It's pretty self-explanatory. New items are inserted at the end of the list. So if you want to find the most recent match included in that list, assuming that you haven't sorted it since, you can use find last to find the match closest to the end of the list. By default, find starts at the start of the list. We can also find the index of a matching element. So lists can be numerically indexed. The first one is object 0. The second one is number 1, and so on and so forth. So you can call find index or find last index. they return an integer instead. So if you're looking for just like the position of the first match. Okay, so using find is very, helpful when we want to get one particular match. If you want to find multiple matches, you can use find all. If you're expecting that there's going to be more than one match. And find all is a great way to filter the records. It's not the only way, but it is a way. And this way you can get a smaller collection of only records that fit whatever criteria you want. And you're in total control over this criteria. Okay, so that's all we have to say about working with searching in the list. We also briefly covered sorting. We are going to cover again sorting with custom sort criteria on your custom object. So that's coming up in a future class. Hopefully all this work with lists today really helps you complete your Lab 1A, because the heart of Lab 1A is that manipulation of the list of coin objects. So now you know how to find matching coins and how to, give a list maybe of coins that are all collected, or a list of coins that have a particular point value, or whatever you've decided to do with your lab. The find stuff is going to be on the test. The test is coming up in 2 weeks. I will put out a test study guide early next week so that you can get a head start on knowing what you need to practice for the test. And keep in mind that your Lab 1A is due this coming Wednesday. So you've got like 5 more days to work on it. And I'm really looking forward to see what you guys can come up with. If you have any questions about anything between now and then, make sure you send me an email. Otherwise, I will see all of you guys next Friday. Hope you guys have a great weekend.